Hello everyone, my name is Sachin. Today I'll be presenting Lab 4. So the goal of this lab was to examine and understand the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. So we'll do this today by combining the fundamental principles we've learned, including both the momentum principle and the energy principle, while also using other concepts we've learned such as Hooke's law. We will see that the spring mass system does indeed satisfy the energy principle. The first thing we did in this lab was obtain position data using tracker from the video that we downloaded offline. We set our calibration stick to be 0.7 meters from the fixed attachment point up here down to the mass hanging on the spring. This was also our origin, where the fixed attachment point was. The mass was hanging in the negative y direction. We set our mass to be our point of mass, and we tracked the position in which it oscillated and swung on the arc. We later saved this position data as a CSV file to later use it in our code. Using position data from tracker, we can also find the spring stiffness. So the formula for one period is this, and we found T to be 1.519 using the position and the plot from tracker. And if we rearrange this formula, we get this. And all we did was simply substitute in T and substitute in the mass, and we found our stiffness to be 6.88 newtons per meter. We can also find the relaxed length. We knew that the mass was hanging on the spring, so that means L was 0.7, and we wanted to find L sub O. And at static equilibrium, the gravitational force and the spring force are equal, and that's why we can actually equate S here, because when the mass was hanging and it wasn't moving, that's a static equilibrium. So basically, we calculate it, and we get our relaxed length to be 0.127 meters. So our system in this lab was the mass, the spring, and Earth, and I'll explain later why the Earth was in our system. So here we just plugged in the initial position data from tracker. We knew the velocity was 0 before Dr. Greco let it loose. Here we instruct Python to read the CSV file that we saved with the tracker data. Here is our time step that we were instructed to set it as 1/210 on line. Our gravitational constant is G. Our spring stiffness we calculated 6.88 and relaxed length to be 0.127. Here Python basically calculates a new length every time by simply subtracting the position of the ball minus the spring. L hat gives you the direction, and S is the stretch or compression of the string. If it's greater than 0, it's being stretched. If it's less than 0, it's being compressed. The next part of our code simply computed system energies. The first one is kinetic energy is 1/2 mass times velocity squared. The second is potential gravitational energy is mass times gravity times position y. And potential spring force, which is 1/2 stiffness of the spring times the stretch or compression squared. So now we're at our calculation loop. From tracker we got our time. We define our initial energies. We have two forces, the gravitational and spring. Spring is simply Hooke's law, negative Ks. The gravitational is only in the y component because the object is hanging in the negative y direction, so it's mass times gravity in the y component. The sum of those two is F net. Here we have the momentum principle, and we have F net, we have the mass, we have delta t, we have the initial velocity, so we can find a final velocity. And we can also find a new position of the ball with the position update formula. So because we find a new ball.pos, we can find the new length every time. And because we can find a new length every time, we can find a new stretch every time, or compression every time. And because we can find a new velocity every time, at every position, we can also find a new kinetic energy. So basically we're updating all the information we know, and simply graphing it down here. I also asked Python to plot a sum of all three of the energies, so let's watch the code run now. Right now I just want to focus on the model. And so the blue dot is the mass, the blue arrow is spring force, the black arrow is gravitational force. The red dot is the position data from the tracker. So basically the blue dot's supposed to follow the red dot all the way, but human error and round off error will always exist, and the red dot is our experimental data, so I can't always pick the perfect tracker position with my point of mass, so that's probably what that is. Let me compare the graphs now, and it'll make stuff a little bit more concrete. This top graph represents model versus experimental position data, with the red being tracker and blue as model. The reason they're probably not exactly the same is because I probably didn't pick my point of mass to be perfect every time, and that's human error that's bound to happen in experiments. And another reason is that the experimental data could have faced drag force when it was swinging around. The bottom graph represents the different energy changes, and the blue line is delta K, the red line is delta US, the green line is delta UG, and the sum of all of them is 0. And because the sum of all of them is 0, which means energy is conserved, that also tells us that the Earth was included into our system and we had no surroundings. We chose everything to be into our system. So for the first what does it mean question, the energy principle is definitely satisfied, and that was because we included everything into our system, the mass, the spring, and the Earth. So delta E was supposed to be 0, and when we plotted these three, it did turn out to be 0, which was represented by the yellow line. So yes, it was satisfied. So for the second question, you're supposed to find the periods of oscillation and just compare them. So I found my x to be that and my y to be a little bit smaller. You just do that from your tracker plots. And they're different, and they're actually supposed to be different. That's because the mass is actually moving in a pendulum motion for the x component and in a harmonic spring motion for the y. The formula to find the period for the pendulum motion is that, and for the spring motion is that. So if you see these two formulas are not related, this is length over gravity, and this is mass over stiffness. So that's why they're different, and they're supposed to be different. That was my lab, and thank you so much for watching.